Okay, so my name is Yoni Toker. Again, I'm sorry for being late. And I'm a researcher from the Nano Institute. My lab is in the 7th floor. If you have questions, then you are welcome to write to me or to come to my office. So the building is building 206. That's the Nano. And the office is 708. So it's on the 7th floor. Section A, and my email, I'll write it down here, but I'll also put it on Moodle. And I'm a researcher in a field called action spectroscopy. Where we study molecules and clusters which are not attached to anything, which are floating in free space, in vacuum. And this is a little different than what usually people do in nano, because usually in nano what people do is take stuff and attach them to surfaces. But many of the questions and the ideas that we think about are similar. In particular, one of the main questions in nano is how do properties evolve with size? And this is a question that we can discuss also in the gas phase using tools of action spectroscopy. And this is what I'll start with today, with telling you a little bit about how properties evolve with size. It's something that we like to call clusters, and then solid-state people call them sometimes quantum dots or nanoparticles, and you'll see that it's all very connected to each other. And I think, did you already have talks in this course about nanoparticles and quantum dots?
Yes.
Yes. So maybe some things you'll see familiar, and some things will maybe be new for you. Okay, so what I'm going to talk today to you about is cluster science. And clusters in this course is not galaxy clusters and stuff like that, but clusters of atoms and molecules. And the original idea to study clusters was to see how properties evolve gradually with size. Okay? So let's say you have a glass of water. So that glass has a lot of water inside. And the properties, and then if you drink half of the glass, then you remain with water with half the volume, but still most of the properties of the water are exactly the same. Except, well, the volume went down and the extensive properties like the mass went down in half, but most of the properties, for instance, the optical properties, are exactly the same. But if you keep on drinking and you reduce the volume again by half and again by half, again by half, eventually the water behaves very differently. Because if you go down to a single molecule, then a single molecule is something that's not the same as a whole glass of water, right? A single molecule cannot be divided again. So what people thought is, let's see the whole transition, how gradually something transits from a glass of water to a single molecule. And so they were thinking something in this order. Let's say, how do I take the board up? Okay, so let's ask, for example, how much energy is in a piece of water. Okay, so you may think that. So let's say we have a drop of water with a certain radius, and let's say how much energy is in this drop of water. Okay, so you may think, well, the energy scales with the number of atoms. Okay, the more atoms you have, the more energy is inside, or the number of molecules. And so you say, okay, the energy will scale with the number of molecules. And the number of molecules scales with the volume, right? So and that scales like r to the power of what? Sorry? R to the power of 3. But, sorry? Thank you. But, so we can think that the energy inside a drop of water will go like something times r to the 3. But on the surface of water, something strange is happening. Okay? Because if you have a droplet of water, then every molecule in the middle sees water from all sides. But molecules on the surface, they don't see water from all sides. On one side there is air, on the other side there is water. So you may have surface effects. Okay? And surface effects, how do they scale? Like r to which power? 2. Why? Because the surface is a sphere. Is the surface of a sphere, it goes like r to the square. So you may think that you have also an r squared term. Now if r is very big, you can ignore this term. But if you have droplets that are very small, maybe this term becomes important. And then maybe more terms become important. So we may think that if we plot the energy as a function of, let's say, r to the 3rd, then at large r it will be just a constant, but when we go to small r, maybe it will behave differently. Maybe it will go down, maybe it will go up, but maybe it behaves differently at small sizes. Yes?
Why it's constant and not linear?
It goes like r to the 3rd. Let's say, okay, sorry, let's plot the energy divided by R3 as a function of R. Okay? So here it will be just A. Okay? But then at small sizes we expect there to be a deviation and for it to be smooth. Okay? And some things really behave this, well, in large R, things behave like this, but when you get to small r, something crazy happens. Okay? And what we'll see is that the energy as a function of r will jump up and down all over the place, will be completely crazy. And this phenomena is something that we call magic numbers. So what we're going to see is that sometimes you take a drop of water and you add just one molecule to it and it can become much, much more stable. Or you add one molecule to it and it becomes much, much unstable. And this is the phenomena of magic numbers. So magic numbers will be numbers of molecules within this cluster where the cluster is very, very stable. Now, I have read in one article that it said that this phenomena should not be called magic numbers anymore. And the reason is that the word magic describes stuff that we don't understand, like something that's not physical, we call it magical. But now we understand this phenomena, so we shouldn't call it magic anymore. In my opinion, it still should be called magic because even stuff that we do understand can be magical. I taught just now a course about polarization, and you take two polarizers and you put them one in front of in 90 degrees and you don't see anything, and then you put a third one in the middle and suddenly you see something. We understand this perfectly, but I think it's still magical. So I think magic numbers is still a good name. Okay, so what I was telling you about on the board is that the idea to study clusters, groups of atoms and molecules, started off by trying to find a bridge between the world of atoms and molecules and the world of big things, which we call bulk. This is actually the whole principle also of nanoscience, to look at what's happening in the middle. And what people realize is that it's not really a smooth bridge. This bridge breaks apart. Things vary in the middle, things happen which are very different than what happens on both sides. Okay, so let me give. So the first thing is, how do you make clusters? How do you make these groups of atoms or molecules of the same sort? And there are two main ways of making clusters. One way is to take a big material and to break it apart into small pieces. So for example, you can take a hammer and you can hit a wall, and pieces of the wall will come flying off in the other direction. In scientific method that works this way is called sputtering. So you can take a beam of ions. So ions are atoms or molecules that are charged, so we can accelerate them very easily. And then we can shoot them on the surface, and then pieces of the surface will fly off in the other direction. So if you take a piece of aluminum, and you shoot it at, let's say, sodium ions, which are very easy to ionize, then you will get aluminum atoms coming off, but sometimes you'll get two aluminums stuck together, so that's an aluminum dimer. Sometimes you'll have 3, 4, 5, so you get clusters this way. The other way of making clusters is to take molecules and glue them together, or atoms and glue them together. And to do that, what you have to do is to take many molecules and cool them down. Because once you cool things down, they start sticking to each other. So a very convenient way of doing this is with something called the supersonic expansion. And most of the experiments I'll show you now were done using a supersonic expansion ion source. So what is supersonic expansion?
This is the second.
This is an example of the second way. So the first way is to take something big and break it down. The second way is to take small molecules and join them together. And in order to cause things to join together, what you have to do is to cool them down. Because when they cool down, they start sticking. So here's a very easy way to cool stuff down. And the idea is, you take a gas that has a high pressure, and you let it expand into vacuum, into low pressure. And what happens is, well, what you can imagine that happens is that in the gas you have atoms that fly in many different directions, but only the atoms that are in this direction will pass through the hole. That's the intuition. So when they pass the hole, you will have many of your atoms or molecules. They will all be flying in one direction. Their speed, can someone guess what their speed is going to be?
What do you like? Typical speed? 100 meters per second?
How's the speed called?
I don't know. I heard
Vacuum.
It's going to be the speed they have inside the gas, right? Which is called the
Thermal speed?
thermal speed is close.
What is the
It's called the speed of sound. Okay, so the average thermal speed is called the speed of sound. That's the speed that sound moves. So they'll move in the speed of sound. So So what we're going to have is many molecules moving with the speed of sound, but they're moving in the same direction. Okay, so they have a high velocity, but the standard deviation or the deviations in their velocity will be very small. So if you're moving in the same frame of reference like them, it looks like they're at the same, they're standing still.
But they're not going to diffuse?
Yeah, they will diffuse a little bit, and that causes even further cooling. So what happens is what diffuses moves to the sides, and then in the middle you have ions that have the same direction, same velocity. Okay, so this is a way of cooling by expansion. Our refrigerators work the same way. We have a gas, let it expand, we produce cooling, and then we have to compress and expand again, and compress and expand again, and that's why old refrigerators would make a lot of noise. But that's how it works. So now we have something moving quickly, but very cold. So if we have a gas balloon that has a pressure of, let's say, 200 psi, so a regular gas balloon, and we expand it into a good vacuum, 10 to the minus 7 torr or something like that, then we can get molecules that are in the degrees of a few degrees Kelvin. So that's very cold. So a few degrees above the absolute zero. So that's very cold, and that's enough to cause atoms and molecules to stick to each other and form clusters. Okay. Why did I put this slide over here? So if you want this to work, then you need a high pressure difference. You need to have high pressure here and very low pressure on the other side. The problem is that if gas is all the time flowing here, then the pressure here is all the time destroyed. So you can do one of two things. Either you can have very powerful pumps to pump all the air out of here. So there are people who do that. They have like a whole room full of pumps to make sure that pressure here is very low. Or what you can do is to close the door. So you only let the gas through in a very short period of time, and then the pressure is not destroyed. So then you have your molecules, but in a given, but for a small amount of time, and that is called a pulsed valve. One of the best pulse valves, well, the best pulse valve you can buy in the world is produced in Tel Aviv University by a professor called Uzi Even. He was the first openly homosexual member of parliament in the Israeli parliament. He only served for 1 month, and then he came back to do science. And besides being one of the greatest scientists here, he's the maker of this wonderful piece of equipment. Okay, so here's a typical experiment that one does with this valve. So you take a gas of xenon, you let it expand, it cools down, the xenon atoms start sticking to each other, and then one does the simplest possible experiment, which is to count how many clusters of every size do you get. Okay? So for instance, they count and they see that they have a lot of clusters of size 13, less clusters of size 14, and you get clusters from all kinds of different sizes. But the big surprise here is that this is not smooth. Okay? Now, what does this kind of measurement tells us? This tells us how stable these clusters are. Okay? Because if you have a structure that is something that is very stable, then it will stick together. If it's not stable, then it will break apart and you won't see it in the end. So these guys here are not stable, they break apart. But here you have something that is relative to them very stable. And then you get a lot of it. Yeah?
How do you measure the clusters?
Yeah, so to measure this, what you have to do is you have to first ionize them.
Okay.
So you shoot electrons at them, then they get ionized. And then you need to, and then you let them into a mass spectrometer. So for example, what you do is you accelerate them, and you count how long does it take them to reach a detector. Okay, and from the time you can measure their mass. And actually, I'm going to talk about these kinds of techniques in the next week. So the most simple experiment you can do is to count how many you have from every size, and what you see is these magic numbers. So, for instance, something, for some reason, it's very, very, very stable at size 147. You add one more atom, suddenly it becomes unstable at all. Very, very unstable. And you see other magic numbers here. Something happens at 55, 13 is very, very stable, and other numbers. So this is the phenomena of magic numbers. I'll give you another example of this phenomena of magic numbers, and this is a much more difficult experiment. This is an experiment that is so difficult that I know only of one guy in the world who does it really beautifully. I know of some other people who tried, and their results are not so impressive. And even that guy is retired, so he's not doing these experiments anymore. But this is an experiment about cluster melting. Okay, so if you take a piece of water, one of the most interesting things that happens to this piece of water is that it can freeze and melt. So if it's below 0 degrees, it's ice, and if you heat it up, suddenly at 0 degrees something happens to it, it turns into water. Now how can you measure this phase transition, this melting transition? So the idea is that you need to measure energy as a function of temperature. Okay, so you take a piece of ice and you start heating it up by pumping energy into it. And what you see is you pump energy into it and the temperature rises. But when you reach 0 degrees, then you add more energy, but the temperature doesn't go up. Why? Because the energy goes into breaking the lattice, breaking the ice and turning it into water. And then you see a jump like this. So if you do the derivative of the energy as a function of temperature, that's called the heat capacity. So here the derivative is constant, here the derivative is constant, but at 0 degrees you have suddenly a jump. That's the phase transition. Okay? So if you open a book about thermodynamics, then they will say that phase transitions can only happen for bodies that have an infinite number of atoms in them. So you can do this for a glass of water, but you can't do it for small clusters. But here's the measurement, and they do the same kind of measurement, like here, but for a cluster that contains 139 atoms. So it's a lot less than infinity. And they see this very nice. So it's not a first order phase transition, but still it's a nice transition. So here it's solid, then there is a jump, and here it becomes liquid. Now if you're not a theoretician, if you're a physicist and you start to think what happens, so over here the cluster looks like something like this. So you have the atoms, they are stuck together in some organized way, like a little crystal. Now you start heating it, the atoms start moving, but when you reach this critical temperature, then suddenly they start moving at random. And then the cluster becomes, from this, it becomes something like this. So the cluster melts. Okay? So this is a very hard experiment to do, but you can do it, and you can see melting of even these small clusters. And the big surprise is that if you study the melting temperature as a function of the number of atoms in the cluster, then it jumps like crazy. Okay? So you can add one atom to a cluster, and suddenly the melting temperature jumps by 20 degrees. Okay, just imagine if you have a glass of water, you add one molecule, and instead of freezing at 0 degrees, it freezes at 20 degrees. It's crazy. Okay, but that's some of the things that happen in the nano and sub-nano world. Okay, so this is a little preview of this phenomenon of magic numbers, and we'll talk about the origins of magic numbers. And but first, I think it's worthwhile to talk a little about the different kinds of clusters that we have, and we usually divide clusters according to the type of interaction between the atoms or molecules within the cluster. So the weakest kind of interaction there is something called the van der Waals interaction. A van der Waals interaction is an attractive force that every two bodies have, but is very, very weak. And what happens, you can think about it as a So what is a van der Waals interaction? So let's say we have two neutral atoms or two neutral molecules. So in principle, they shouldn't have an interaction between them. But let's say there is a fluctuation of charge. So within an atom, we have a nucleus that is positive, and we have electrons that are negative. And typically, both of these cancel each other out. But let's say that for a short instant, the electron moved away a little bit. So now this molecule has a dipole. Okay? Then what happens? The plus pushes, there will be an electric field in this direction, which will push this plus in this direction and this minus in this direction. And now there is an attractive interaction between these two. So this is our picture view of a van der Waals interaction. It's very, very weak, but it's something that every two bodies have. So for example, I showed you before an experiment on xenon clusters. Xenon is a noble gas. A noble gas is all the electrons are in a closed shell, so it doesn't want to form chemical bonds with anything. But two xenon atoms can interact with a van der Waals force. It's very, very weak, and therefore you can only see this happening at very low temperatures. So if you want to, for example, if you want to pass from a neon gas to a neon liquid, it will only happen, I think, at 80 degrees or at a very low temperature. And that's what you also need to form clusters. Okay, so let's now think about let's say we have xenon atoms and we want to form clusters of them. So a cluster with two atoms will look like this. You have the two atoms and they're touching each other. Okay, so can someone guess how a cluster with three atoms look like?
Triangle.
We say a triangle?
Or one in the middle and two on each side.
What's your name?
Moshe.
Moshe. Okay, so Moshe has suggested two ideas for how a cluster with three atoms will look like. Moshe, suggestion B is in one line, and let's call this Moshe's suggestion A is a cluster that looks like this.
Or is a V shape.
V shape?
Exactly like what you
Okay, this is Moshe's suggestion number 3. Okay, so can anyone guess which of these shapes will we find?
The bottom one is water. But I think we have all of them. No?
Okay, we can have in principle all of them, but which is the most stable?
The one with the highest surface tension?
Okay, highest surface tension. Someone else can. Okay, let's have a guess. Who says A? Raise your hand. Who says B?
No, it's this thing. I think it's.
Who says C? Why C?
Pretty much between B and C depends on the valence electrons, but usually you will have lone pairs, so it's probably BC. But again, it's
Okay.
more.
So this is just van der Waals, no lone pairs. What's your name? Sapir. Sapir, you said A. Can you say why A?
Maybe because all the molecules are connected.
Okay.
They are connected between all.
So let's look at at the connections. So in structure B, this atom in the middle has two connections. Okay, but this atom in the side has only one connection. So it takes only you need to break only one van der Waals bond to break this apart. Okay, but in this case, every atom has two connections. So if we define the binding energy, as the energy to detach one of the units, or one of the atoms, or one of the molecules, then this one will have twice the binding energy as this one. Can you see that? Okay? Yeah?
You assume that the binding energy is the same in case A and case B, and
Yeah. And then
there's
van
no
der Waals,
interconnections.
right. And the van der Waals interaction, this is a good approximation. Okay? When we get to covalent bonds and stuff like that, hydrogen bonds, then it's not true. And then you have water which has a shape like this. Okay? But in van der Waals, then roughly the energy is just depends on the distance. Okay? So that's the governing feature of van der Waals interaction. Okay? So if you have a cluster with 4 atoms, what will be the structure? Yeah, so you can put another atom on top and they form a tetrahedron. So now every cluster has 3 connections. Three. So its binding energy will be 3 times the binding energy of a diamond. Okay? And so on, you can start building larger clusters. So if you want to know what the shape of these clusters are, for a good approximation, you want to find the shape that has the most connections. Okay? And this is similar, not identical, but similar to a mathematical problem that's called the packing problem. The packing problem is how can you pack things as dense as possible. Okay? You have a bag of oranges. What is the smallest volume of the bag? Okay? If you have the most connections, then also the volume will roughly be the smallest. Now, the first person that we know that was really interested in this problem was Johannes Kepler, who was famous for the Kepler laws, and he said that for an infinite number of oranges, then the best way to pack is called this hexagonal closed packing that looks like this. This is how we really pack oranges in carts. But it turns out that if you have a smaller number if you don't have an infinite number of oranges, if you only have, let's say, 50 oranges, then the best way to pack is in shapes like this that have a 5-fold symmetry. And they have an icosaedral symmetry. So for example, you can put one in the middle and then surround it with 12 other atoms that each lie on the vertices of an icosahedron. Then every atom here will be connected to 5 other atoms on the icosahedron and will be very close to the atom in the middle. Okay? So this is an icosahedral structure, and then if you count how many atoms you have in total, you'll get the number 13. Okay? So in this case, the binding energy will be roughly 6 times the binding energy of the van der Waals binding energy, because every atom has 6 neighbors. If you add one more atom to the cluster, what will happen? You have to put it over here, and then it only has 3 neighbors. So it's much, much less bound. So this gives a magic number. Okay? Then the next magic number after 13 will be 55, and the one after it will be 147. And these really are magic numbers that you see in experiment. 13, 55, 147. The other magic numbers are a little harder to explain, but for example, if you take 2 icosahedrons and merge them together, then you can get these 71 and 87 and so on. Okay? So these kinds of magic numbers are called magic numbers that come from the geometry of the cluster. Okay? Now, not all clusters have the shape of icosahedron, but many clusters are governed by this van der Waals. So these numbers is something you see a lot in nature. Okay, also for molecules. If you take a molecule like SF6 that has a spherical shape, then you'll see the same magic numbers. Okay, any questions? If you take salt, for example, so what is salt? Salt is made out of, for instance, the salt we eat is NaCl, so it's sodium, which is positively charged, and chlorine that is negatively charged. And then if you look for the best way to arrange clusters of salt, then they like to arrange in square structures. So then the magic numbers you see is the magic numbers that are the cubic numbers, the numbers to make cubes. And you also see that in experiment. Okay. But there's also magic numbers you see that come from a totally different reason. And this is an example of the same kind of experiment done on sodium clusters. So you take sodium, you evaporate it, and you cool it down, and it forms clusters, and you see some very nice magic numbers. You see 8, 20, 40, 58. But it's very different than all the magic numbers you saw so far. So how do we understand these? Yeah?
Basic question. How would you, why the magic number 20 is a magic number, and let's say you have like the 2 picks below?
So these are,
right?
so this is just, it's a mass spectrum, so you don't see what's, so this is 19 and this is 20, right?
Yeah, but if you go like 4 lines to the right, you see another so-called...
Yeah, so this is arguably a magic number. But what you see is that after 20 there's a huge drop, okay? After 40 there's a huge drop. But yeah, you're right, sometimes it's a matter of interpretation. What you can often do is you can do systematics. So you can vary the temperature or the pressure and so on. And what you'll see is there is a general trend, and on top of it you see the magic numbers. And the general trend may change, but the magic numbers will not change. So then you see which are the magic numbers. But yes, there is also a matter of interpretation. And you saw that for the xenon there is many things that are magic, and some of them are not even understood today. When you plot this in a log scale, then 58 becomes much more prominent. On a linear scale, it's hard to see because you look at this, but then... Okay, so how do we understand sodium clusters? So sodium is an nice example of metal clusters. And in metal clusters, the way we think about metal clusters is that the electrons within the cluster are shared throughout the whole cluster, just like quantum dots or metallic nanoparticles. So we have the atoms. Every atom donates its valence electrons. Do you know what a valence electron is? Okay. So in the case of sodium, sodium has one valence electron, and so each atom donates one electron to the cluster, and these electrons are like a blanket that surrounds the atoms. Okay. But so now we have a cloud of electrons. And this cloud of electrons can form shells just like the electrons within an atom. So electrons in an atom, they also form magic numbers. So if you have two electrons, then you close the first electronic shell, and then you get a very stable atom called helium, right? And then you can keep on closing shells, and every time you close a shell, you get a very stable atom. In this case, the noble gas atoms. So something similar is happening with metallic clusters. So every atom donates electrons, and these electrons fit together into electronic shells, and every time you close a shell, you get a stable cluster. The difference, however, between the periodic table and clusters is that the order of these shells is different. Okay, so the shells are the same. So for instance, the first shell is 1s, which has 2 electrons. In atoms, the next shell is 2s. But in clusters, the next shell will be 1p. Okay? And then 1d, and then and only then 2s. So the order of the shells is different, but it's the same shells, and you can see it. So when you close 1p, so the first shell has 2, and then the second shell has 6. So when you close the second shell, you get 8 electrons. So the cluster of size 8 should be very stable. That's what you see in experiment. And so on. So 20 will be the closing of 2s, and so on. So this experiment was the first to present this idea of electrons being shared throughout the whole cluster, and this became known as the Jellium model. Why is it called the Jellium model? Because we don't care at all about the geometry of the atoms. Okay, we don't. So the atoms are like a jelly, and the electrons are shared throughout this jelly. And one of the consequences of this Jellium model is now you have like a gas of electrons that is within the cluster, and this gas will have nice optical properties that you can calculate very easily. And one of the things the consequences that you can, if you have larger clusters and you have electrons that are delocalized on a larger area, and then they will have longer, their optical absorption will be on longer wavelengths. And this is something that you can see very easily in experiment. Did they talk to you about optical properties of nanoparticles? So the first who actually did experiments on this is the early Romans. So the early Romans had a recipe how to color glass. This is an example of a Roman cup. It's called the Lycurgus cup, and it's a glass that has a nice color, and actually the color of the glass depends on the angle at which you pass the light through it. But the Romans didn't know what's the origin for this color. The person who realized the origin is Michael Faraday, the great scientist best known for his work on electricity. But he realized that what gives the glass the color is nanoparticles of gold that are within the glass. So you can take gold, and if you make large nanoparticles, they will have a color that is more to the red. And if you make the nanoparticles smaller, then they'll have a bluish color. So by varying the size of the nanoparticle or the cluster within the glass, you can change the color. So now we see so I think now we understand these magic numbers that you see with sodium, and then we can go back to the experiment on melting of sodium clusters, and the first guess would be that these clusters are very stable, so they will melt at a higher temperature. So we should see melting at these sizes. I think I'll skip on how the experiment is done unless you ask me about it. Okay, so they tried to see if the magic numbers you see correspond to what you see from melting, and they found no connection whatsoever. And can anybody guess why there's no connection? Why? I mean, if something is very stable, shouldn't it melt at a higher temperature?
They didn't find connection
between the magic numbers where you get a lot of many very stable clusters from the Jellium model, so where you complete electronic shells, and the melting temperatures. So you would expect that if you close an electronic shell, you have a very stable cluster, so it will melt at a higher temperature.
Yeah, but once you take out some some atoms, it will break down. So it's like
Maybe electrons are not stable as what you showed us before. They don't act like a symmetric bulk.
Okay, that's one suggestion. Maybe someone can ask another, can suggest something else? So I think the key point that it's okay if you don't understand, because the guy who did the experiment, his name is Helmut Haberland, one of the smartest people, I think, in science. I think the reason he didn't get a Nobel Prize for this is that nobody else could do these experiments. Because you usually get a Nobel Prize if you start a new field. But these experiments were so hard that nobody could continue this work. So, but it took him a long time to understand what's going on. But the key insight is that the melting is the behavior of the atoms, of the atom position. So the properties of the electrons don't matter so much. Okay? So now when you talk about the melting, you actually need to look at the arrangement of atoms. So then the question is, what will be the arrangement of atoms? So here it comes back actually to the packing problem. So you have electrons, and they're like a cloud around the atoms, and they want to cause the atoms to be as dense as possible. So once again, the atoms, their shape will be an icosahedral shape, where the volume is the smallest. And it turns out that the melting temperatures really correspond to these icosahedral packings. So if you have a packing with an icosahedron, then it melts at a high temperature. If you add one more atom, then the symmetry is broken, and then it melts at a much lower temperature. It's less stable, and so on. Okay, maybe the most beautiful experiment in cluster science that had a huge impact on nanotechnology is an experiment done by these three guys. And it all starts with this guy called Harold Kroto. And he was interested in how molecules are formed in outer space. And so in order to understand that, so the main thing that Harold Kroto did until this moment was trying to identify molecules in space. So space is very cold and mostly empty, but there are many atoms in space, and you can also find a lot of molecules. And you look at their spectrum and you try to identify them and in Harold Kroto's time, they really started identifying more and more molecules. So they find CH and C2H4, and they discovered more and more molecules. Sorry?
What is the origin of the molecules in space?
That's a very good question, and that's exactly the sort of questions they ask. But it turns out that you have atoms, and the atoms collide, and sometimes they form molecules, and sometimes these molecules collide and form bigger molecules. So you have very interesting chemistry that happens in space. So he wanted to model it. He wanted an experiment that does the same thing. So what you want to do is you want to something very empty like outer space. So that's a vacuum system. You put atoms inside and then you cool them down because space is very cold. So supersonic expansion is the way you can make it. Okay, so you have a gas of helium expanding. It's a low temperature. Then you add to it atoms that like the atoms in outer space. And the atoms that he was interested was carbohydrates. That's molecules that are made of carbon and hydrogen. But they discovered when they were studying these carbohydrates that even carbon by itself makes something very interesting. Okay? So if you do the experiment just with carbon, no hydrogen, and you measure the distribution of cluster sizes, then at high temperature you get something like this, which doesn't look very impressive. One thing you may notice is that the jumps here are of 2. So from 60 you get to 62, 64, there's no clusters of size 61. Okay? And this actually makes a lot of sense from point of view of chemistry, because if you want to have an odd number of carbons, then it has to be a radical, and this is not stable, and so on. If you don't know chemistry, then don't mind. Okay? But you may notice that there is a little bit of variation here. And that's when someone asked me before about magic numbers, then this is where you start doing systematics. And what they could do is they could lower the temperature. And as they lowered the temperature, something strange started happening. And they see much more of this size here and a little bit of this size here. And it turns out that this size here is exactly 60. And this size here is 70.
Buckyballs are around 60, no? Atoms.
And when they cooled it even further, then they got that everything is of size 60, only a tiny bit of size 70. So the story is that later this evening they each went home and thought, where is this number 60 coming from? And Smalley, he just got a computer program where you can start drawing structures. And he said, okay, carbons, they like to have each atom either 4 neighbors or 3 neighbors. That's called the sp3 or sp2 hybridization for chemists. So let's see if every atom has 3 neighbors, what kind of a structure can we make? And he started drawing and he ended up with this structure over here. And the following, so the nice thing is every atom really has 3 neighbors. And if you count the number of atoms in total, you get 60, which is what he saw in the experiment. So then next morning he comes to the lab, he shows it to the other 2 guys. So Smalley is the guy with the experimental setup. Kroto is the guy who suggested the experiment. And Curl is the guy who happened to be with them in the same room and got a Nobel Prize just for being in the same room. So, no, he's the guy who got the other two to work together.
The glue.
He's the glue, yeah. So Smalley called friends of his that are mathematicians and asked them, what is this structure? And they said, this is a truncated icosahedron. So I showed you an icosahedron before. If you start cutting the corners of an icosahedron, then you can get this shape. But then they said, don't call it a truncated icosahedron, you can just call it a football. Because if you look at a football, then the football has the same structure. It's made out of pentagons and hexagons, and every vertex here has 3 neighbors, and if you count the number of vertices, then it's exactly 60. So these guys, they wrote an article about it, and they put this picture on the article, and they wrote in the caption, a football in the United States is called a soccer ball on Texas grass. So they took the picture on a grass, but you don't really see the grass in the photo. Anyway, they wrote the paper, they submitted it to Nature, it was accepted, and they got a Nobel Prize for this. And I think, why is this worth a Nobel Prize? Because once you realize that you can take carbon and you can roll it up into a ball like this, then people realize there's a lot more stuff that you can do with carbon. So for example,
Carbon nanotubes and stuff like this.
yeah, so if you cut this in the middle, you can add another row of hexagons. And then if you count the number of atoms, then you get 70. So this is the peak over here. But then you can add another row and another row and another row, and you get a nanotube. Or you can roll it up into, just have hexagons and roll it up into a surface, and that's called graphene. Another Nobel Prize from recent years. So, so they realized there's many crazy things that you can do with carbon. And this is really one of the biggest advantages in nanotechnology, the idea that you can make all these structures. So fullerenes, nanotubes, graphene. If you stack graphene up, then you get the regular form of graphite. And you can have diamond, or you can have disordered carbon. And in terms of impact on the industry, then in the beginning they thought, so these are called fullerenes, also known as buckyballs. Why? Because they reminded Smalley of the architectural work by an architect called Buckminster Fuller. So they called these structures Buckminster fullerenes. And then people they usually abbreviate them and call them either buckyballs or fullerenes. And they thought that, in the beginning, they thought that this would be very useful for industry. For science, it definitely was very useful because you can have, I mean, most of the clusters I've shown you so far are stuff that only exists in the lab. But this thing, you can make macroscopic amounts of it. So when you burn a candle, you have a lot of buckyballs. And in Heidelberg, there is a scientist, I forgot his name, who made an industrial method where you can make a material that's made only of these fullerenes. So then you can do science on a very specific molecule. It's also the biggest molecule that was identified in space. So that ties into the whole story. So they thought that this would be also very useful for industry. For example, as a lubricant. A lubricant is something when you want very low friction. So you can take a lot of balls like this and you get something with low friction. It didn't end up having any important commercial uses. So one time when they, I don't remember which, I think Kroto or one of his students was giving a talk about it in front of the British Parliament. Then one of the members of Parliament said, "So what are you saying? This is the most fascinating molecule that is completely useless." And that shows that in the British Parliament, people are a little smarter than in the Israeli Parliament. But nanotubes have huge applications in industry. So nanotubes, the nice thing about them is that they're very strong, but they're very light. They're hollow. So you can make bicycles out of them, you can make bulletproof vests, you can make elevators to the moon maybe one day. And they also have tunable electronic properties. So, and graphene now is the hottest material in electronics. Okay, so maybe the last thing I'll tell you about is water. Okay, so probably the most important clusters that you can hear about are water clusters. And the reason water clusters are very important is that you find them in many, many places. One of them is in biology. So our body is how much, 90% water or something like that. And many of the important molecules that govern life are proteins that have water inside them. So the way that water interacts with itself determines the structure of proteins, which determine the behavior of our body. Another place where water clusters are very important is with the atmosphere. So there is a guy in Jerusalem called Nir Shaviv. And he's in very good touch with a guy from Denmark that I forgot his name, I'm sorry. And they both of them claim that many of what you hear regarding climate change is not accurate. Why? Because the current climate models, they don't take into account clouds, and clouds have a huge impact on the environment. And there's a way to see it. So what happens is, when our solar system moves around in the galaxy, then sometimes it moves into regions where there's more cosmic radiation. It's called the spiral arms of the galaxy. And then there's more ions coming from space. They produce more clouds, and then this affects the climate. And this, actually, Nir Shaviv found that it correlates with the ice ages. So you can explain the ice ages by the movement of our solar system in the galaxy. Now the problem, how is the fact that the movement of Earth correlates with the temperature? Well, it goes through clouds, and to form a cloud, you have to have water, which is in the air, condensing into a droplet. But the problem is that it's like blowing a balloon. If you have a balloon, then the step that is hardest is the beginning of making the balloon, right? So if you try to push air in the balloon, the first stage is the hardest stage. And this is in forming droplets called nucleation. So you want water molecules to form together clusters, and the clusters to start growing into water droplets. The first stages are the hardest, and they happen more easily if you have some pollution in the air, if you have other molecules, or if you have ions. So when you pass through a galaxy, you have ions. The ions are nucleation sites, and droplets grow there. So, so understanding how the behavior of water clusters and how they form into droplets is very important, and it's not a trivial point. So how does water work? So water has an oxygen connected to two hydrogens, and the electric charge is mainly, the negative charge is mainly on the oxygen, and then there is positive charge on the two hydrogens. So then if you have another molecule over here, then the negative charge of the other oxygen likes to be close to the positive charge in this hydrogen. And then you start forming networks. So you want to make maybe another water molecule that's its O minus is here, and H plus goes like this, and then you try to form chains with a maximum number of connections. The problem is that there's millions of different structures like this, millions of different isomers. So if you have different charges here, if you have something that's not water, then it will change all this network. And that's the difficulty of doing all these experiments on water clusters. So the magic number will change, and the stability of these clusters will change very dramatically depending on what's in the middle here.
But it's also correct for other clusters if you put another ion inside them.
Yeah, sometimes you're right and sometimes it's not. So for example, metal clusters, most of their properties are from the number of valence electrons, so you don't care so much about impurities. Less. You care less. In Van der Waals, anyway, everything is neutral. Okay, you're partially right, but with water it's more dramatic than anything else. How do you make water clusters? So this is another example. Most of the ion sources I told you about so far were sources where you, like supersonic expansion, where you take stuff and collide it together. But in this case, it's easier actually to start with big water and break it apart. And this is a source called electrospray. So the idea is you take a syringe, machat, and you pass water through it, and then you apply a high voltage on it, like 4 kilovolts or something like this. So this voltage, what it does is it pushes the water in this direction, but the surface tension of the water so you have water inside, but because of surface tension, the water becomes like in the shape of a cone in the middle, and from the tip of the cone you get droplets. And that's called a spray. And this is a way you can put a coating on your car. If you want to paint your car, you can use spray like this, or you can pump this spray into a vacuum system. So then you have droplets of water that go into the vacuum system, and then if you heat them up, then the droplet starts evaporating. So if you don't heat them up, you get a large droplet, but if you heat them up more, you get smaller and smaller droplets. Eventually you get single molecules. So this is called electrospray, and this is a way to form water clusters of any size you want. I think we'll stop today here, and next week we're going to go into experiment, and I'll give you a course on ion traps. Thank you and see you next week.
Thank you.